Welcome to the Deep Dive. Today we are zeroing in on a really big challenge in developing large language models. We're talking about getting these models to move beyond just, surface-level answers and into truly complex, multi-step reasoning. And specifically, how reinforcement learning with verifiable rewards, RLVR, plays into this.
Right. RLVR has definitely been a key part of many reasoning breakthroughs we've seen. But the research we're looking at today identifies a pretty fundamental problem, a systemic failure point, really.
Yeah, this idea that LLMs just hit a wall, like a performance
Yeah.
plateau. After only a few thousand optimization steps, the model just kind of stops getting better, even if you pour massive compute power into it.
Exactly. And the diagnosis in these papers for why this happens, it comes down to something called sparse exploration patterns.
Sparse exploration, meaning they just don't look around enough during training.
That's the core issue, a scarcity of, let's say, meaningful exploration. And today, we're digging into a framework designed specifically to try and break through that plateau. It's called DeepSearch. And it really proposes a fundamental shift in the optimization strategy.
Okay, a shift from what to what?
Well, instead of just scaling training depth, which, basically means running more and more training steps, hoping for improvement at meditation, it focuses on scaling training breadth. So encouraging systematic, much more structured exploration across the whole potential solution space.
Right. So our goal here is to unpack how Deep Search actually pulls this off, specifically how it integrates Monte Carlo Tree Search MCTS directly into that RLVR training loop, because that sounds like more than just a small adjustment. It sounds like a pretty big structural change.
It absolutely is. And the promise is unlocking, well, potentially significant performance gains, especially in tricky areas like mathematical reasoning.
Okay, so let's start with the bottleneck itself. Sparse exploration. Lay that out for us.
Well, the current RLVR methods, they tend to rely on very limited sort of local rollouts during the training process. You can maybe picture a model trying to navigate a huge maze. During training, it only explores a few turns right near its current spot.
So it never really gets a sense of the whole maze structure.
Pretty much. Because of that limited view, it often completely misses these critical, sometimes longer reasoning paths that are absolutely necessary to solve complex problems.
And there's an irony here, isn't there? Because when we actually use the model at inference time, we expect it to perform these really sophisticated, broad searches. We want it to navigate that whole maze effectively on its own.
Right. But the way we've been training them doesn't systematically build that capability. We haven't given it the right tools or the structured practice during the learning phase.
And the cost of that, it's not just theoretical.
Mm.
The sources show what happens when you just try to brute force it, right?
Yeah.
Just scale up the training time.
They did, and the results were, well, not great. They saw really negligible returns. They actually burned through, I think the number was 1,883.2 GPU hours trying to push one model further.
Wow.
Yeah. Only to confirm that essentially the performance had plateaued, just running it longer was incredibly wasteful and ultimately ineffective.
Okay, so that really underscores why we need algorithmic innovation, not just more compute. Which brings us back to deep search embedding MCTS into the training loop. How does that provide richer supervision?
So by integrating MCTS, the model isn't just learning from the final outcome, like whether the answer was right or wrong. It starts learning from the entire process of exploration that MCTS performs the branching, the evaluating, the selecting paths. It gets visibility into the structure of the search.
So it's learning how to search, not just what the answer is.
Precisely. And that directly addresses that core problem of sparse, inadequate exploration during training.
So moving MCTS from just being an inference tool to being part of training, that's the first big conceptual leap?
Yes. But the Deep Search team realized that standard MCTS, or more specifically its usual selection algorithm, UCT, isn't really optimized for learning efficiently during training. It's built for execution.
Okay, so they couldn't just plug and play standard MCTS. What did they change?
They developed what they call a hybrid selection strategy. This replaces the standard UCT approach for deciding which path to explore next within the MCTS tree.
Hybrid, meaning it combines different approaches.
Exactly. It keeps part of the standard UCT, what they term local selection. This is still used for the sort of principled comparison between sibling nodes when you're expanding the tree locally.
Makes sense. Keep what works for local decisions.
But the real innovation is the other part, global frontier selection.
Global frontier.
Oh.
Okay, what does that mean in practice?
So think about standard MCTS again. You typically traverse from the root down to a leaf node, evaluate it, backpropagate, and then maybe start another traversal from the root. Global frontier selection changes that dramatically. Instead of just looking down one path, it looks at all the current endpoints, all the leaf nodes, or the frontier across the entire search tree simultaneously.
All at once, across the whole tree.
Yes, and it selects the single most promising leaf node globally to expand next, no matter which branch it's on.
Huh. That sounds like it would really change the dynamics of the search,
Mm-hmm.
focusing on the absolute best next step anywhere in the tree.
It does. It shifts the focus towards making progress across the entire breadth of the search space much more effectively.
Now, to make that global comparison work, they need some way to score those frontier nodes. They use this frontier priority score, 5 honors. Can you break down what goes into that score? How does it guide the search?
Yeah, the score 5Lers is quite cleverly designed. It essentially balances exploration and exploitation using 3 main components.
Okay, what's the first one?
The first is quality potential. This basically looks at the value of the parent node of the leaf you're considering. In simpler terms, it encourages the search to prioritize expanding nodes that stem from already promising paths. It's like saying, let's dig deeper where we've already found some gold.
So that's the exploitation part. Stick with what seems to be working well.
Exactly. Then the second component is the uncertainty bonus. This is all about exploration. It uses the policy's entropy, which measures how uncertain the model is about its own prediction at that node. A higher bonus is given to nodes where the model is less certain.
So it actively pushes the model to explore the areas it knows least about, to reduce uncertainty.
Precisely. It prevents the search from getting stuck in a rut, exploring only familiar territory, and forces it to investigate riskier, less-known paths which might hold the actual solution.
Okay, quality potential for exploitation, uncertainty bonus for exploration. What's the third part?
The third is a depth bonus. This one's pretty straightforward. It encourages the search to go deeper into the tree.
Why specifically add a bonus for depth?
Well, particularly in tasks like math reasoning, you often need to follow a sequence of steps quite far to actually reach a conclusion and verify if it's correct. Without this bonus, the search might be biased towards staying near the root, where things are simpler but solutions aren't found. This pushes it towards completion.
And the research showed this hybrid strategy, especially the global selection part, actually worked better.
It did. Their ablation studies confirmed it. Using this global frontier approach actually reduced the average number of MCTS iterations needed to find a solution compared to vanilla UCT.
So it's more effective and more computationally efficient
Just
by making smarter choices about where to explore next.
Right. It avoids redundant traversals down less promising global paths.
Okay, so the search is smarter. Now, how does the model learn effectively from the results of that search? You mentioned credit assignment.
Yes. Once DeepSearch completes an MCTS iteration, it uses something called heuristic score backup to update the values of the nodes in the tree. And there's a specific constrained update rule they use, often cited as equation 7 in the paper.
A constrained update. Why constrain it?
Think about a long reasoning path. Maybe the first 9 steps are perfectly logical and correct, but the 10th step makes a mistake, leading to a wrong final answer. Standard RL might assign a 0 or even negative reward to that entire path, including all the good intermediate steps.
Which means the model might unlearn those good steps, right?
Potentially, yes. The constrained update rule in DeepSearch prevents that. It ensures that the value estimates, the Q values, for those intermediate nodes on a path that eventually leads to a correct solution can only increase or stay the same. They never decrease due to a later mistake on a different path.
So it protects the knowledge of good intermediate reasoning steps, even if one attempt fails later on. That sounds crucial for complex problems.
It provides much more fine-grained and stable credit assignment. But learning isn't just about reinforcing success. What about learning from the failures?
Good point. Does DeepSearch have a specific strategy for that?
It does. They call it expansion with entropy-based guidance. This comes into play if an entire MCTS search iteration fails to find any correct solutions. Instead of just randomly picking a failed path to learn from or ignoring them, it specifically looks for the most confident negative example.
The most confident failure. What does that mean?
It identifies the incorrect final node, the failed endpoint, that was reached via a path where the model had the lowest average entropy.
Low entropy means the model was very certain about its steps along that path, even though it led to a wrong answer.
Exactly. It's like finding the mistake the model was most sure wasn't a mistake.
So you focus the learning on correcting the model's biggest, most confident blunders.
Precisely. These are considered high-value training targets because they represent the model's most misleading internal certainties. Correcting those gives you the biggest learning signal.
Okay, this all sounds very sophisticated: smarter search, better credit assignment, strategic learning from errors. But we have to come back to the cost. MCTS is computationally heavy. Isn't running MCTS for every training example just incredibly expensive? How do they make this practical?
That's a key question, and they addressed it with some really smart engineering, mainly through their adaptive training strategy.
Adaptive how?
Well, first, they don't run MCTS on every problem. They use iterative progressive filtering. They maintain a hard subset of the training problems. This subset includes only those problems where the model's current success rate, they measure it using pass 1 at K, is below a certain threshold, like, say, 25%.
So MCTS is only deployed on the problems the model is currently struggling with.
Correct. The MCTS compute is focused purely on this dynamically changing hard set. As the model gets better at certain problems, they fall out of the hard set. As new challenging problems arise, they enter it.
That makes sense. Concentrate the expensive search effort where it's actually needed.
It keeps the training adaptive and targeted. And there's a second piece to the efficiency puzzle.
Which involves the replay buffer.
Yes, cache solution usage. The system stores any verified correct solution trajectories found during MCTS in a replay buffer. Now, if a problem comes up in the hard set, but the system sees it already has a cached correct solution for it in the buffer.
It doesn't need to run a full MCTS search again.
Exactly. It uses what they call a hybrid rollout strategy. It takes the known cache solution path and maybe supplements it with a few standard, much cheaper rollouts. This completely avoids the cost of a full MCTS run for problems it already knows how to solve.
Okay, so combining that adaptive filtering, only using MCTS on hard problems with caching the solutions, seems like it would cut down the computational overhead massively.
It really does. And that efficiency is critical because it allows the algorithmic benefits of deep search to shine through without being drowned by prohibitive compute costs.
Which leads us nicely to the results. What did this approach actually achieve on those mathematical reasoning benchmarks?
The results were quite strong. Deep search achieved an average accuracy of 62.95% across the 6 different math benchmark suites they tested on. And this established a new state-of-the-art for reasoning models in that 1.5 billion parameter class.
62.95%. How does that stack up against what was considered the best before?
The previous top model, which I believe was called Nematron Research Reasoning Twin 1.5B V2, scored 61.70%.
Okay, so Deep Search delivered a solid improvement of about 1.25 percentage points.
Yes, and importantly, the sources emphasized that this gain wasn't just on 1 or 2 specific benchmarks. The improvement was consistent across all 6 of them: AIM, AMC, Math, Minerva, Olympiad.
That suggests the improvement is quite general, a result of the better exploration strategy, making the model fundamentally better at deduction.
That seems to be the implication. And then there's the efficiency story, which is maybe even more striking.
Right, you mentioned the GPU hours. How many did Deep Search use to get this state-of-the-art result?
Only 330 GPU hours?
330. Okay, now let's contrast that again with the brute force attempt you mentioned earlier.
Right, that baseline approach that just tried scaling the training duration, that consumed 1,883.2 GPU hours.
And it's still only plateaued at 62.02% accuracy, which is lower than Deep Search.
Correct. So Deep Search not only achieved a better result than new state-of-the-art, but it did so using 5.7 times fewer GPU hours than that extended baseline training run.
Wow. That is a dramatic difference. It's really powerful evidence for the idea that smarter algorithms can beat brute force compute scaling, at least in this context.
Absolutely. It validates the core idea that strategic, broad exploration during training is vastly more resource effective than just trying to run an inefficient training process for longer.
So the big takeaway here seems to be that Deep Search really managed to bridge that gap. We talked about the gap between the complex search we want at inference time and how we actually train the model.
It successfully taught the model how to perform structured search as part of the learning process itself.
And the sources seem to conclude that this points towards a necessary shift in how we think about developing these reasoning models.
Yes, the conclusion seems to be that the future isn't solely about making models bigger or just training them for longer. It's about fundamentally rethinking the structure of the learning process itself. We need to build in the capabilities for systematic, sophisticated reasoning right from the start, mirroring what we expect the model to do when it's actually put to work.
It suggests that this kind of systematic exploration isn't just a nice-to-have addition.
It might be a fundamentally more effective and certainly more computationally sound strategy for pushing the boundaries of what LLMs can do in complex reasoning.
Okay, a final thought then for you, our listener, to chew on. If this shift in training strategy focusing on how to search yielded such significant gains with nearly 6 times less computation just in mathematical reasoning, what other complex reasoning domains might be unlocked if we focus on teaching models the process of exploration, rather than just optimizing for the final answer through sheer computational repetition? Something to think about.